Alright, this is to go with another video where I was talking about, I had my drawings and I was talking about magnetic waves and how the electric factor is just, a particle, like a photon particle flying through space. There's no wave aspect to it. And then the magnetic part is kind of a wave, but this wave is made up by the oscillation of other particles in response to the photon flying through, basically. And so there's no like the waves themselves are not waves in a field so much as they are just the macroscopic effects of particles, right? When you zoom out, you see a wave, but when you zoom in, it's just particles moving back and forth, right? So, to kind of go along with that, I didn't really give a good explanation for why the particles move towards more energy rather than towards less energy, because in theory, the flow of gravity, the flow of dark energy is towards areas of less energy. So if there's less energy, that should be pulling, dark energy is flowing to fill that void, right? So you would think that maybe the particles should actually go towards where there's less energy, because they're just going to follow that flow. But sorry. From what I've found from my thought on this is basically they don't do that because there's not actually any necessary grand flow happening there. The dark energy is there. It doesn't necessarily need to flow into that point. What we what we see as this dark energy, it's the creation of these virtual, self-annihilating virtual particles, and that is like this dark energy, and so basically, the dark energy is already there, and after the photon passes through, there's no, stray particles, virtual particles, or virtual photons chilling there, but they start to pop up and appear again as time progresses. And, this is very fast because it's on such a tiny scale, but we're getting tired now. It's still observable. The difference is still a factor to bring into play. And so what I have written here is that faster particles have less mass but more energy, and so are more affected by the gravity of smaller particles, allowing them to move towards them at a faster speed. So that ties into my faster speed, smaller mass, and kind of adds in that extra part of just playing into, larger mass versus slower speeds, faster speed versus lower mass, and like this kind of balancing. We said you're more likely to catch things in a bigger net, but you have to give up some speed there, and that speed is. You maybe ask, well, why is the speed vary? What is causing that speed to vary? And I think that it is basically this explanation here, which is effectively gravity is causing these changes in speed, and so a smaller mass is more attracted. So let me show you my image, and then I'll get back to what I said there. So this is my drawing that I made here to kind of show this. So all those little specks are the virtual photons around, we'll just say any given particle. And so the arrows pointing in is the, qualitative strength of, or like qualitative value of energy in any direction. So the photon just passed by over here, and so there is less virtual particles on this side, and so the amount of energy on this side is qualitatively lower than on this side, than on this side, than on this side, right? So what happens is since there's less particles here, the gravitational pull on this side is lower than the gravitational pull of all of these photons, right? So because the gravitational pull is weakest on this side, it gets pulled in that direction, right? Because the pull from this side and this side is equal, but on this side there's an imbalance. And so it gets effectively pulled towards higher energy, which is, as we know, energy and mass are pretty much the same thing. So it goes towards where there is higher energy. And this motion is caused by the pull of, the gravity of the particle itself compared to the gravity of the collective particles here. And so the smaller this mass is, the more comparable the forces here. And so instead of it pulling these towards it more than it moves towards them, it starts to move towards them more than they move towards it, the smaller it gets. And so when it's moving towards them more and more, that's when it gets a faster and faster speed, and that's when it has a smaller mass. But when it has a larger mass, that's when it's pulling more towards it. And as I said, it makes more sense to have a larger mass because when you're flying by, you would be flying through something more like this, and so you want to try and pull in as much as possible when you're in a deprived state. So you want to have an increased mass to pull more towards you, and you're willing to accept a slower speed in order to get more energy. And so this is pretty much what's happening with these particles. And we don't like to think of gravity on such a small scale, but gravity is driving everything, because gravity is just basically dark energy and energy flow. And it really just goes back to kind of entropy and stuff. But we see black holes absorb mass, and we see them grow in size as they absorb mass, right? Well, what do you think's happening there? This is the same thing. This is the exact same thing. It is absorbing mass and gaining energy, because a bigger black hole has more energy, right? Because in theory it has more mass, right? So, getting into this again, just to explain it, the photon will move away, right? It'll go towards where there's more energy, but then this particle will move towards where there's more energy. But at a certain point, the energy will look more like this because there's another particle right over here. And so it goes, oh. And so as it moves this way, it moves closer to another particle. There becomes less and less pulling it that direction. And then all of a sudden, this side has more than this side does, right? And so then it starts moving back that way. And so this oscillation back and forth of getting pulled towards energy this way and then getting pulled towards energy this way is what is causing this back and forth oscillation. And this back and forth oscillation of this particle causes the next particle to move back and forth. And that is what we see as magnetic waves. But the magnetic waves are being driven by particles, and these particles are being driven by gravity. And this gravity is just energy differentials, basically. But yeah, so I think that I covered everything that I wrote here. But I think that that makes a lot of sense. Right? Like, I don't think that that is some outlandish claim to make. It works based off of simple principles of just, we know how gravity attracts stuff. So I don't really see this being an issue. And, when I was thinking about this and, after thinking back towards, again, smaller mass, faster speed, that kind of tied in. And it does make sense that, it would get pulled it would get pulled faster and be able to move faster if it has a lower mass, but maintain that same energy, right? It would still maintain that same energy because, again, it's keeping that rate of energy consumption as it moves, but it's having smaller mass is allowing it to move at that speed, right? Because if it gains mass, it's slowing down. It's going to have to slow down. And we just observe that on the large scale. Like, that's what we see. More massive objects take more energy to move. And I don't know. It just to me, it just makes sense. And it's stuff like this where I kind of put these things together, and I didn't necessarily think this to begin with, but it just kind of falls into place with what my original grand scope is. And the more I think about this, the more I refine my theory and the more sense it makes and the less crazy I feel, because I really don't see why this would be wrong. It does, I mean, maybe I'm ignoring some serious issues here, but I don't think so. I think that it's covering all the bases pretty effectively. So I guess we'll find out. But I'll add this in here too. I just recently found out about this thing called laser cooling. And I did a talk about lasers producing magnetic fields because, they're creating this lack of energy, basically. And, that's what kind of these magnetic fields are. Tying back in with this, that goes to that talk. But I found out about laser cooling and I was like, wait a minute, laser cooling. And so, basically with laser cooling, you have to cool down a particle by stopping its motion. And its motion is only stopped in the direction the laser is coming from. And so from what I saw, they explain this by the wavelength of the laser is Doppler shifted, when the particle is moving towards it, and it's not Doppler shifted when it's flying away. So it can move away, but it can't move towards, and it gets stopped in that direction. And I don't think that that's right. What I do think is right is what I'm saying here. In the direction the laser is coming from, there is less energy. And so the particle doesn't go that direction. In the direction that the laser is not coming from, there is more energy. And so that's the direction it goes. And so the laser has no effect on it traveling in that direction, but going back towards the laser, that's when, the atom or whatever starts to have issues. And, again, why does no motion mean no energy? Because the particle or atom is cut off from any points of higher energy, and so no longer can afford to emit radiation at the same rate. And so what we see as, this movement of the atom and this heat coming off the atom is radiation. And so when we try and cool it down to, absolute zero, we're basically trying to stop it from emitting any radiation whatsoever. And so, in order to freeze it and cool it down, what do they have to do? Well, they have to shoot it with lasers, right? And these lasers, like I said, the laser, in the direction the laser is absorbing all the energy that's there, and so there's not much energy for the atom or whatever to absorb energy, and so it doesn't flow in that direction, and it tries to move in a direction to absorb energy. But if you put lasers in every direction, all of a sudden there is no direction that the atom can go to, absorb more energy. And so what does it do? It doesn't go anywhere, because there is no gravitational force pulling it in any direction, because there is no virtual photons for it to get pulled by. So it just stays still. And then since it's not moving, it loses its energy, because again, the only way it maintains its energy is by absorbing more. And so as you put these atoms in these lasers, they realize, oh crap, I got no more energy coming in. I've got to stop sending energy out. And so it goes into a conservation mode and stops emitting energy, because it still has to maintain its internal energy of whatever that atom is. That atom has a certain temperature or a certain energy level that it has to maintain in order to sustain its structure. And, when it can no longer maintain it, that's when atoms decay. But what happens is that these lasers cool them down to so very close to basically absolute zero, but they can't actually get them down to absolute zero. And the main reasoning, I think, for that is because even though there is a significant amount of lack of energy provided to the atom, it is very difficult to make that value zero, right? And so that is why we are still seeing just the slightest amount of temperature still. But again, this temperature is the radiation being given off. So if you were able to get it down to absolute zero, what that would mean is that that photon is no longer emitting energy. And if it's no longer emitting energy, that means that it no longer is, able to absorb sufficient energy. And if that's the case, then, if you were able to get an atom down to effectively absolute zero, it should just decay. It will no longer maintain its structure. It'll decay because it needs energy. It needs to be constantly cycling energy. And so if you get it all the way down to zero, it may not decay instantly, but it will decay. We can't actually get it down to zero yet, from my understanding. So you can't prove me wrong there. But if we did find a way to create a powerful enough laser to do this, or whatever, that is my prediction. And if that does happen, everyone will be like, whoa, what's going on? And I'll be like, exactly. But I don't know. Maybe it's not possible. Because to make the amount of energy available, you don't need to necessarily make it zero, but to reduce it that much that there's not enough energy is difficult. I would recommend trying to do it with heavier atoms. Try and do it with heavier atoms, like do it with lead. I think lead is the heaviest atom that's not already radioactive, right? So if you can turn lead into a radioactive atom, you you know you did something, right? So that would be my recommendation, is try and do it with the heaviest atoms, because in theory, if my theory is correct, they need the most energy, and so cooling them down should be easier because they require more energy to sustain themselves. And so, long story short, try it with lead. Let me know what happens. Maybe it won't. I mean, it probably wouldn't be able to do it with like a block of lead, because of how effectively lead is at like blocking stuff. But like a few atoms of lead, I would imagine you'd be able to make it radioactive. I don't know. We'll find out, I guess, right? I don't know. But you know, this is why you need a laser. You know, why does no motion mean no energy? Because the particle or atom is cut off from any point of higher energy, and so no longer can afford to emit radiation at the same rate. This is why you need a laser pointing at the atom, front, back, top, bottom, left, and right, because then there is no direction of higher energy / more mass, and the particle stops moving, but still has its internal energy and base cycling rate to keep it from absolute zero. All particles emit radiation, and if you were able to get it to absolute zero, the particle or atom would decay. The Bose-Einstein condensate is a result of matter packing so tightly together to maintain their energy at such cold temperatures that they are seemingly one object. As I said, a higher density object is effectively doing that because it is... Actually, that would be an interesting thing to test. Like, what happens if you put like a block of lead in, you know, liquid nitrogen or something, and you measured it before you did that and after you did that? Does its mass, would its mass increase? Its density should increase, but would that make its mass increase? In theory, no, right? Because you're not changing the amount of molecules that are there, you're just changing how tightly they're packed. So in theory, the mass shouldn't actually change, but its density should. I don't know how you measure density without just calculating it, but if you can measure density in some way if you can measure density, then, you know, I recommend trying that as well. Like lead in normal, lead in liquid nitrogen, see if there's a difference in density. I mean, you could really think about it like, now thinking about that, we know that when you quench a blade, right, that tends to make it stronger, because that, you know, I'm assuming that makes it more dense, right? That might be some more backing to my theory there, but I don't know exactly what the mechanics are behind quenching, but thinking about dipping one metal into a cold substance made me think of that. So, basically, density increases because the temperature, like when there's less energy available, the density has to increase in order to, as I said, maintain their energy levels. And this goes back again to this description here. You know, if you imagine this is an atom as there becomes less and less dots, they got to get close. They will pull closer and closer together. And when there's effectively basically no dots, they'll almost be touching, right? Because there's nothing in between them. But they will behave as if they're just one object at that point, because they'll basically be touching, and you can't distinguish them. But what's really happening is that they've just absorbed all available energy to a point that they have run into each other, and now they're almost like feeding off of each other, maybe, and absorbing every little scrap they possibly can, because otherwise they would decay. And again, I don't know what kind of experiments have been done, but I recommend trying a dense, non-radioactive material and seeing what happens. My theory is that it does become radioactive. Maybe it doesn't become radioactive. Maybe it just gets frozen, and it doesn't do anything. But I don't think that makes sense. I don't think that that's the logical outcome. I think that it probably should decay. But I don't know how that would look, right? Because if it's so low in energy that it barely, it's that tightly packed, when it does decay, where does it go? It's kind of my thought process, right? If it's that cold, it would decay, but would it go anywhere? I mean, I don't know if it would. It would just boop, and and then it would be like, yep, nope, still cold. So I probably wouldn't move very much before it realizes it's still too cold. I don't know. Anyway, I think that was my last talk. I did a bunch tonight, and I probably talked more than I should have. My throat's feeling raspy, but I had a bunch of things to kind of get through, and when I kind of hit this eureka moment with that, I was like, I need to talk about that. Yeah, so peace out.